Our system is a single well system, which is opposite the 2 or 3 wells normally seen in EGS. It's also a vertical system where the well itself is acting as the injector side, and the production tubing in the well where the heated fluid returns. We start to create massive hydraulic fractures. At about 10,000 feet or 12,000 feet, as much as a half-mile long on either side of the well. We fix the connections between the well and the reservoir. Fluids freely flow outwards and then come back in. This creates a T-shaped junction, which is hydraulically inefficient, which you try to flow fluids. Very long structures, a few feet in height. We force fluids out of the well. Fluids are flowing outwards or along the top half of the fracture. Because we're using massive fractures, higher sweep efficacy, we're able to use fewer fractures and base over 1,000 feet.
Welcome to Geothermal Unleashed, the podcast where we dive into the frontier of geothermal energy and its role in the global energy transition. I'm Elizabeth Cambry with the Valorec New Energies team, and I am here to help spotlight the innovators, technologies, and stories that are driving geothermal forward. Today, I'm delighted to welcome my guest, who is Jeff Spray, the founder of DTS, and we've got some exciting technology that we are going to talk about today. So to get our show kicked off today, Jeff, I would like to have you start by introducing yourself. Give us a little bit of an introduction on your background, your education career, and how you came to be a part of the geothermal space.
Sure. Thank you. And it's nice to be with you, by the way. So this started from a family background in oil and gas that goes back to the 19 teens. And I took on an interest in drilling, at which point my parents said they wanted their college money back, by the way. And that led into, learning that field, learning some service work. Family had a supply business in Central California, learned that area. And then got into business development for some specialized drilling technologies that led to technology development, then to actually move to Houston, and then ultimately to geothermal applications for technology in tubular areas I was developing.
So how long have you been in the geothermal space?
You could actually say going back to the 1980s in a way, but seriously on the technology side since the early 2000s.
Wow, so you've had a lot of time to think about geothermal technology.
I would say so, yes. Yeah.
So let's dive into what we're going to discuss today, which is DTS, your company's enhanced geothermal systems technology. So can you describe it and maybe high level share with us how it differs from the mainstream approach to enhanced geothermal systems?
Sure. Our system is a single well system, which is opposite the 2 or 3 wells normally seen in EGS. It's also a vertical system where the well itself is acting as if you would say, the injector side, in our case, the inlet side. Then the production tubing in the well where the heated fluid returns is essentially the production side of the well.
Okay, so what problem is DTS trying to solve in geothermal, and what led you to rethink the traditional enhanced geothermal systems model?
Yeah, I really, obviously, geothermal suffers from limited production, and that's what we've always had an eye on. And I was told quite some time ago that EGS, has its challenges, and as anything does. And so ultimately, what we've, I guess, discovered is that we've kind of bridged the gap between the productivity capabilities of hydrothermal and with its scarcity, however, with the, say, more ubiquitous resources that HDR, hot dry rock, has, but difficulty in producing, and kind of merge those together.
So most people have heard that geothermal often needs multiple wells. You need an injector and a producer. And you said that your approach claims to deliver the same or better performance with just a single well. So can you explain how that's possible and then why it matters.
Sure. The productivity is not only about the well's output, it's really about the restrictions or the parasitics that take your growth production. So we are actually building bigger, deeper systems, hotter systems, in some cases 2 or 3 orders of magnitude more than what's being done heat-wise, depth-wise, fracture size-wise. And then our process or our method gets rid of the parasitics, which may take easily 40% of your gross production. We are also able to maintain the heat flow, which enables us to use higher efficiency conversion methods. So we're taking out everything that's detracting from from geothermal production and redesign to where it's now all working in our favor.
Okay, but can you explain to me and to our listeners, how do you do EGS with a single well? This might not be easy for everyone to understand because
Sure.
we're just
Yeah.
used to seeing an injector well that you frack and it's connected to a producer well.
Sure. Sure. So our system, what I failed to mention is that from the vertical well at about 10,000 feet or perhaps 12,000 feet, we start to create massive hydraulic fractures. And these may be as much as a half-mile long on either side of the well. So what we've done is fix the connections between the well and the reservoir to allow the fluids coming in from the surface to freely flow outwards away from the well and then come back in, which we'll get in more detail later. So we
Okay.
do that.
Oh, no, go ahead, please go.
Uh, well, we do this upwards of 15 times in average 600-degree rock. And we are making a massive system that with that type of temperature can only produce.
Okay, so let's just take your wellbore. You would put, so you're saying like 16 stages of fracking you would have in the single wellbore?
There are 15 in a full design, 15 massive fractures in place over a approximately 21,000 foot interval.
Okay, okay. So conventional EGS has struggled with high injection pressures and the energy penalty that comes with that. What
Yes.
causes those high injection pressure losses, and then how does your design nearly eliminate them?
Sure. The conventional approach is, of course, to either directionally or horizontally pierce the fracture with the wellbore series of or a few wellbores. This creates what's called a T-shaped junction, which is hydraulically about the most ineffective or inefficient type of structure you can use which to try to flow fluids. Additionally, when fractures are made and through that involving that type of structure, they are very often what's termed tortuous fractures, where they are incomplete. And then actually, it's not the injection part, it's the recovery aspect that may be asking fluids to be returned to the surface through maybe only one perforation or one crack connecting this large fracture volume. So
Okay,
in our case,
can
sorry.
I make sure I understand, and then I'm going to have you continue. So when you say a T-shaped hydraulic connection, are you talking about just the fact that you've got your horizontal well and you've got fractures that are intersecting them?
Well, yes, if I might, hopefully this will want to work. This is our well, and
Yeah.
this our fracture here. We're running this way, so the T is looking like this. So in our case, what we do is align the fracture height with the vertical well's trajectory, and instead of relying on one or two tortuous connections, indirect connections, we're actually supplying hundreds, if not even a couple of thousand perforations to freely engage the well and reservoir. So fluids are able to flow out freely without injection pressure, also return without the use of pressure.
So are the fractures that you're creating more, they're not like thin fractures, they're going to be more connected fractures that you would.
No, the what we're after is creating fractures in impermeable rock, hence the
Okay.
depth, starting depth. Ours look just like anybody else's.
Okay.
In terms, everybody's ultimately is a large crack on either side of the origination or of the original perforation.
Okay. Okay, I understand. One of DTS's novel feature is its flow diverting barriers. So what are these? How do they work? And how do they help you control where the geothermal fluid travels underground?
Sure. So the barriers are actually a cornerstone of the technology, and these are either chemical or other types of structures that are made through the length of the fractures. They're actually, very long structures, and actually surprisingly very short in height. They only need to be a few feet in height. And so what happens is we force fluids out of the well through also part of our system, which is a thermally compliant packer system, which allows the production tubing to move with different changes in heat. Those force fluids out, and where we basically have created a channel along the top half of the fracture where the fluids are flowing outwards along our barrier. And then the barrier stops. There's an open spot at the end of the fractures where the fluids then turn and come back to the well in the same manner they left.
You're placing an artificial barrier between an upper fracture and a lower fracture. How do you make sure the two get connected?
Well, there's a simple explanation, which is very difficult to understand without a picture, especially, is that they using chemical methods, which are just using water conformance or water control techniques
Yeah,
from oil and gas, been around before you and I have,
I'm familiar.
and or at least before you have. And the the way to look at it most simply is if you drained your fracture, leaving only half of its fluid there, you can then pour chemicals on top of that, and it will flow out accordingly. And it's all calculated volumes as you would do with any downhole process. And then that fluid, gelling or setting fluid, will materialize. Then you have your barrier. Now, alternatively, we can use the native rock as the barrier by employing fracture diversion techniques or fracturing diversion techniques that we can actually frack around the native rock and connect that way by using old gravity fracture and other types of methods also have been around for quite some time. We are just literally laying a line, an impermeable line across the center elevation or the middle elevation of the fracture, what it boils down to.
But maybe not injecting enough water shut-off technology to reach to the end of that fracture so you don't
Yeah, yeah,
completely
and
isolate it.
even if you do, reach the end, you simply refract and reconnect the system.
Has anything ever been done like this before?
There's debate about that. There are some water control references that talk about 1,000-foot plugs and greater. They're not well referenced here, and it's a bit of an area that we say in essence has been done as everything else we're doing component-wise. Technology has been done. What has been done is that type of work and the type of heat we're talking about, of course, with geothermal, perhaps to the dimension to which we want to develop there. But we say it's been done.
Okay, so I'm curious, have you modeled this before? And I'm interested to understand the surface area that you're creating. Is it similar type of surface area that you would get with a traditional EGS producer or an injector producer um, well pair?
In terms of like I said, the fracture's a fracture. You can tune them according to their dimensions, the height, the width, the length, and so forth. Of course, you can use higher quality materials. In our case, because we are wanting a self-circulating system to eliminate the pressure parasitic, we use high roundness, high quality ceramic proppant materials.
Yeah.
that coincidentally enable flow better and, of course, last longer.
So then you would inject and produce through that single well. So you'd
Continuously
inject.
on a base load manner. Yes,
Okay.
yes. And actually, we're not injecting, we're just recirculating. It's injecting itself, it's
Right.
self-flowing.
What kind of rates are you flowing at?
I'm sorry, race, the modeling work we've done, yeah, we went upwards of 1,300 gallons a minute or a little over 82 liters. So,
Okay.
so
Okay.
and I'm sorry, we've ranged starting out the low end of 500 and found that 1,300 is optimal for economics purposes.
Okay. So a reoccurring theme in the geothermal world is that heat can't recharge fast enough when their fractures are too closely spaced. So how does your design address this?
Sure. Well, the first part that happens with the exhausting the heat is everybody takes too big a bite. They're too aggressive on what's being extracted. And it's not really the rock's fault. You know, the rock is what it does, what it does. In our case, we are able, because we're using massive fractures, because we have a higher sweep efficacy, we're able to use fewer fractures, less than a quarter of what most others do. And therefore, we are able to adequately space the fractures so as to allow the heat to replenish and operate in a baseload manner. In our case, that spacing is over 1,000 feet, which actually should be more, but that's something of an optimal
Okay, so when you
number.
say sweep efficiency, just so that I'm clear and I make sure I understand and our listeners, so you're talking about fluid placement across the interval that you fractured. So evenly placing that fluid, and that's important because then you're reaching all the surface area so
Correct.
that you're not just having one channel where you've got to break through. Why
Exactly. Or
does
it's known as a
your
short circuit, right? Yeah.
Okay, so why does your fracture design create a higher sweep efficiency? So you've said at some point in our discussions, 90% is what you could achieve. So why? How does your design lend itself to such a high sweep efficiency?
Yeah. We want to say 100%, but we
Okay.
also say we're somewhere in between. Back to the notion of supplying hundreds of perforations there. What we found in our modeling is that we could vary, and we did this actually on our and showed the effect. We can vary the perforation's geometry, its quantity, and its placement so as to cause different behaviors as the fluids exit. And even the first time around, that 90% factor is what we showed just on our very first guess, actually, by what the effect could be by supplying all this relationship between well and reservoir and the vast number of perforation connections. So I should add that we can also vary the elevation of our barriers so as to change that behavior in the above and below chambers.
Okay. So one major claim is that DTS can maintain heat adequate to sustain a flash system at surface, your surface equipment. Can you elaborate on this?
That comes back to the sustainability given by the spacing matter, in that we are able to maintain heat flows in certain range over the long term, which is exactly what flash systems want or need to operate properly. The ORC gives you, variability or on-off functions, but you lose efficiency or you trade efficiency for that. Ours is less variable, or the preferred system is less variable, but we are talking about 3 orders of magnitude or in that neighborhood increased production net.
Okay. Now, this is my favorite question.
Aha.
Your early stage modeling shows around 30 megawatts electric from a single well, which is far higher than anything I've seen in hot, dry rock geothermal wells. What reservoir conditions, design features make this achievable? What are you doing differently?
Sure. Well, the first part, these are big wells, big diameter wells
Like how
that
big?
uh, surface pipe wise, they're 20, 22 inch, down to 80% of world record levels, down to that 10,000 foot layer. Underneath that, we would set unconventional 14 or 15-inch OD size liners. And so it's adequate, especially at temperature, to move the type of volumes at 1,300 gallons, for instance. That's the final product. The beginning is, again, we are dealing with a massive system, and orders larger than what is conventional in terms of fracture sizes. We're also working with temperatures that are double. We are, at least in full design, getting near the 500 sea level of where we would be extracting. But we're also extracting, by going vertical, you're getting more total heat. So we start at 300 degrees, roughly around 10,000 feet, then work our way down and then back up. So there's that. Then the spacing, allowing the base load. So we've obviously doubled or more our overall production that way. Our use of the higher conversion system, and then the having been rid of the parasitics. So everything is net on that basis.
Okay, very interesting. Oh, I'd be very curious to look at your design. All right. 30 megawatts electric is a lot, so something to be looked at. Let's talk durability. With a single well system, people might worry about redundancy. How do you ensure reliability and long-term performance without multiple connected wells?
Yeah, I look at this as fewer being better, less complicated. I also look at it as potentially being the equivalent of, say if you had a 3-well EGS system, something, if you're looking at reliability, it would be the equivalent of perhaps towing 2 cars behind your main car. So you always have some kind of backup, but you're doing that at the detriment of the first. And of course, you've spent 3 times more on cars than you maybe don't have to.
Okay, so DTS also proposes producing 30 megawatt electric as seasonal energy storage. How does this work?
Yes, it's not storage in the conventional sense. Obviously, to start the system and the geology has ready to go heat when the time comes to employ what we're calling storage. What we're doing is actually rearranging our production curve, and which has shown that we could, instead of conventionally just to produce baseload, you would just start out a certain rate and just continue and down a normal decline curve over years. In our case, we're adjusting the output to be able to do the 30 net for, it came out to just a day and a half, less than 90 days. And then we also see that if we could let it recover then for 9 months, again, back to the spacing issue, with adequate spacing, it could be virtually fully recovered. It would actually be at upwards of a little over 98% 9 months later in time for the next season.
Okay, so I'm going to shift gears a little bit and I want to talk about cost. So, how does your simplified design change the cost profile?
Sure. Well, the first advantage is when your output is way higher, you are spreading out your costs. So you automatically have a very large advantage that way. But then backing up, we are getting rid of the cost to run injection, the cost to do cooling. We've also understood that plant-wise, say if the example we were given with a 15 megawatt plant versus a 30 megawatt plant, you can actually double your production, but your labor and so forth doesn't double. You could literally only add 2 or 3 more people and have the same function. It's just that everything bigger is the only real difference. So those being the chief reasons, and the cost is as low as any type of any type of power source.
Okay. Can you clarify one thing for me? How are you eliminating costs that are associated with injection and pumping?
It's literally, we're running on vacuum. The modern turbines can run down to a little bit under 220F, at which point it's not much of a leap to get back under boiling. And in our system, because we have this 10,000 foot upper zone that is not used that is actually able to draw a vacuum on the system. And then, but we're also at one point creating a hydrostatic value, and then the system is off and running at that point.
In general, how much is like injection costs, pumping costs?
I've seen anywhere from 28 to 40% of gross production.
Oh, wow.
It's
Okay.
big. It's a big, big advantage to not have to do that. And
Okay.
then we've not talked about the cooling part, which
Yeah.
is 10 to 15% more off the top. So
Okay. So there is so what you're saying is by using a flash turbine, that's more cost effective than using an ORC because you eliminate the cooling cost of an ORC?
cheaper for capital, cheaper for operation, and puts out substantially more net.
Okay. Okay. Because you can get higher efficiencies with a flash turbine versus an ORC.
Absolutely, absolutely.
Okay. Okay. But there's some downsides, right, to flash turbines? I'm not an expert on ORC or flash turbines.
I guess you could say there are downsides to everything, but
There
here
are.
the benefits far outweigh
Okay.
that. I'd actually let me tell you one well-known individual, who unfortunately just passed away, told me also years ago that at Imperial Valley, for example, we have some of the worst fluids in the world that
Yeah.
they run those directly through turbines. And he said the maintenance program would consist of every 2 years shutting them down for a week, inspecting them, and knocking the mineral off.
That
I
would
mean,
be interesting
you
to
know,
learn more
and
about.
when we're working in a relatively pristine system, it would have silica, of course, but nothing like
Yeah.
you would see, in hydrothermal environments.
I think maybe I'll have to do a podcast about the maintenance of the flash turbines at the Salton Sea. Oh, that could be interesting.
Why not? The ORC guys won't like it so much, but
There you go. Okay, so my last question for you today is looking ahead. What's next for DTS? What milestones do you need to hit to move from modeling into full-scale commercial deployment?
yeah, we go back and forth on these substantial opportunities that come our way, and that are in terms of our nine-figure opportunities, and then those tend to disappear. We go back to the traditional route of proving concept. However, as I mentioned earlier, that pretty much the concepts have all been proven. There's really more a matter of tuning already known properties and practices in terms of materials and, back to the water conformance type of areas. So I say that, of course, the preference is to jump in on the larger opportunities who, interestingly, they don't care about the normal technology development path. They just want their power, which is why they were talking with us. And they wanted a clean power, I should say. And so that would be the preference. So perhaps a middle ground to answer your question is what we need are the resources to develop these larger projects, which there are no shortage of course, especially with everything going on currently.
Yeah.
So,
Okay, well, I want to thank you so much for joining me today. It's always fun to learn about ways that individuals and companies are innovating in this space, and you have a solution that I haven't heard about before. So I want to thank you for taking the time to share with us more details about it. And I want to thank all of our listeners for joining us on this episode of Geothermal Unleashed. I hope today's conversation with Jeff has offered fresh insights and has sparked new ideas about the future of geothermal energy. As we continue to navigate the energy transition, it's clear that geothermal has a powerful role to play, one that's only just beginning to be fully realized. Until next time, keep challenging assumptions, exploring new frontiers, and working together to unlock the full potential of geothermal energy. Thank you.